Hey everyone, and welcome. Today we're going to peel back the layers of Java and get right down to its core. We're going to see how just a few simple ideas, logic, repetition, and data are used to build all the incredible software we rely on. So let's pull back the curtain and see what really makes Java tick.
So, have you ever stopped to think about that? When you look at some complex app on your phone, what's really going on under the hood? What are the absolute fundamental pieces that make the whole thing work?
Well, it really just boils down to these three things. Seriously. First, you need the ability to make decisions. That's your logic. Then, you need the power to do things over and over again without getting bored. That's repetition. And finally, you need a way to organize all the information you're juggling. And that's data. That's the whole shebang. Let's break them down one by one.
All right, first up is logic. You can think of this as the brain of your program. It's that spark that lets your code react differently to different situations, which is what makes it feel, smart. The most classic tool for this is the if-else structure. It's basically a decision tree. The program asks the first question, hey, is this character a capital letter? If the answer is yes, great, its job is done. But if it's no, and only if it's no, it moves on to the next question. And it just keeps going down the line until it gets a yes or hits that final else at the bottom. This guarantees that one and only one path is taken. Now, if you find yourself writing a super long if-else chain, and they're all checking the same variable, well, that can get messy really fast. That's where the switch statement is a lifesaver. It's built for exactly this situation. One variable, many possible values. It's just so much cleaner and way easier to read. To use a switch statement right, you gotta know these three key words. Each case is one of the specific values you're looking for. The default is your safety net, for when nothing else matches. But the one you absolutely cannot forget is break. Without it, the code finds a match and then just keeps right on going, executing the code for all the other cases below it. The break is the stop sign that says, okay, we found our match, we're done here. Okay, next up, repetition. If logic is the brain, then loops are the muscle. They're the tireless workhorses of your code, doing the same boring task thousands or even millions of times, and they never get tired and they never complain. This right here shows the one huge difference between a while and a do-while loop. Look at the while loop on the left. It checks the condition before it does anything. In this case, since 12 is not less than 10, that code inside never even runs. But the do-while loop, it runs the code first, and then it checks the condition at the end. That means a do-while loop is guaranteed to run at least one time, no matter what.
Now, what if you know exactly how many times you need to do something? Maybe 10 times, or maybe once for every item in a list. Well, in that case, the for loop is your best friend. It packages everything up, the starting point, the stopping condition, and the step, all in one clean, readable line. It's the go-to for counted repetition.
And don't let that simple structure fool you. For loops are crazy flexible. You can count up, you can count down, you can go one at a time, or you can jump by threes or even hundreds. You can even put loops inside of other loops to make grids or cool patterns. There's even a continue keyword that lets you say, skip the rest of this round and just jump to the next one. It's an incredibly powerful tool.
All right, on to our final building block, data. You've got the brains with logic and then the muscle with loops, but you need somewhere to store and organize all the information you're working with. This is how we bring order to all that chaos.
Two of the most common ways to hold a bunch of stuff in Java are arrays and array lists. The difference is all about size. An array is like buying a shelf with exactly 5 slots. Once you build it, it has 5 slots, and that's it. It never changes. An array list, on the other hand, is like a magic bag. You can just keep putting things in it and it'll grow as much as you need it to.
And sometimes a single list just won't cut it. That's when you need a 2D array. The best way to think about it is just like a spreadsheet. It's a grid. And to get to any single cell, you don't use one number, you use two, the row number and the column number. Simple as that.
Okay, everybody listen up, because this is a trap that gets almost every new programmer. When you see a line of code like nums2 equals nums1, your brain might tell you, great, I just made a copy of the array. But you did not. Not at all. What you've actually done is create two different labels, nums1 and nums2, that are both pointing to the exact same array in memory. Think of it like putting two different street signs on the corner that both point to the very same house.
So let's see what happens. We're going to use one of those names, nums1, to go into that house and change something on the wall. We'll change that first element from a 10 to a 99.
And look at that.
Because both signs point to the same house, it doesn't matter which one you use to find it. When you look at the array using nums2, you see the change that was made through nums1. It's a shared reference, not a copy. Remembering this will save you so much headache down the road.
Okay, we've seen logic, we've seen repetition, and we've seen how to handle data. Now for the really fun part. Let's put all these pieces together and see how they form an algorithm to solve an actual problem.
So here's our challenge. You're given two numbers. How do you find the biggest number that divides into both of them perfectly? Let's check out two different ways to solve this using the building blocks we just talked about.
The first method is the one you'd probably think of first. It's the brute force way. You just start a for loop that checks every single number, starting at 1. Inside that loop, you use an if statement to see if that number divides both of your inputs. You just keep track of the last good one you find, and when the loop's over, you've got your answer. It's simple, it works, but for really big numbers, it can be pretty slow.
Now, this second method, the famous Euclidean algorithm, is way more clever. Instead of checking every number one by one, it uses a while loop and this really cool mathematical trick with remainders. It just keeps dividing, finding the remainder, and then swapping the numbers around. It's kind of magical how quickly this process zeroes in on the right answer.
And this really gets to the heart of it. The first method is all about direct checking. The second one is about smart manipulation. That's what efficiency in programming is all about. Finding the clever shortcut instead of just trying everything.
So there you have it. From a simple if statement all the way up to an elegant algorithm, we've seen how these core ideas, logic, repetition, and data, are really the Lego bricks of all programming.
Every app, every game, every single piece of software you use is just a creative combination of these very simple concepts. The tools themselves are basic, but what you can build with them is truly limited only by your imagination. So now that you have the building blocks, what are you going to create?